respect to swap of x and y. So, and indeed, so this term is symmetric, the swap of x and y. So this is actually nothing but negative dy plus dx. So it's the same expression as you see here. And then, so the tricky part is the random walk bridge of fixed length, fixed level drop, and which must cross the zero level only once. And if you ever worked in random walks, there is one very well-known transformation of proceeding from a direct random walk into its dual random walk, which just swaps the increment. So if you look at the random walk which takes the increment starting from the last one till the first one, so the trajectory of this random walk will be just the original trajectory rotated by 180 degrees. So basically, if you rotate this trajectory, so it sort of swaps the endpoints. If the original trajectory was level crossing once, so then the rotated trajectory will do the same exactly once. So, and this consideration of dual random walk, in other words, rotating the trajectory, gives you the same type of random walk bridge. So I'm plugging that once you swap x and y, this part stays the same. So this argument shows you that in this expression now is p substituted for q. The formula is invariant on the swap in x and y, and that's it. So that's how we established the fact that this measure is stationary. So now I have very few minutes, possibly 6, most maybe 10 minutes for the remaining part. So now, if you have questions, so please do ask. Otherwise, let me just add that, so, as I said, to the best of our knowledge, so that's the result on station distribution, but so far it's not unique. So if you want uniqueness, so an easy way to prove uniqueness is to prove convergence to this very distribution in some metric. Now we're getting into the topic of convergence. And for convergence, we need to impose some additional assumptions. So far, everything was general. So the assumption will be that the random walk is either arithmetic, as on the left-hand side. So Sk is either arithmetic or spread out. So, and what this spread outness means? It means that there is a step at which random walk acquires density with respect to the Lebesgue measure. The law of Sk, starting at 0, has a non-singular component. Okay, so this means that the distribution of the random walk eventually smooth this out. So, and under this assumption, so we have that the total variation distance of our chain started at x so the total variation distance between our chain started at x and the station distribution converge to 0 for every point in the state space. So unfortunately, so this is the best and only result of convergence we have so far. So some assumptions are necessary, so some smoothness assumptions. So why this assumption is necessary? Because basically, if you have this assumption, so then it's possible to show that for any starting point, the transition so there is a separate proposition which says that if you look at the law of our chain starting at some starting point x, so if you look at its absolute continuous component and take the derivative with respect to the station distribution, or if you wish this reference measure lambda plus, then this density will be positive at every point x and y. So, and this proposition, which follows from either of these two assumptions, guarantees you that the random walk is the Markov chain is irreducible. In other words, from every starting point x, it can get with positive probability into any set if the pi measure of this set is positive. So that's the usual assumptions. The usual assumption when you deal with convergence of general state Markov chains. So once you have this, you can prove this convergence in total variation. So if you don't have this assumption, so then the total variation distance is not the right distance. So if you want to prove convergence, you would probably do convergence in some other norm, in some other metric between distributions. But the problem is that there are very few results of convergence of Markov chains in different metrics. So there is a recent approach by Martin Heyer and Jonathan Mattingly, which does convergence in Wasserstein type distance metric. But the conditions they apply, the conditions they impose, they don't apply to our chain. So literally nothing works. The only possibility is to deal with total variation convergence, which is too strong, of course, but not so many other methods. And basically, these assumptions are designed, roughly speaking, to work with total variation convergence. So the last result which we have, but I don't want to write down, is the rate of this convergence So we know that this convergence is exponentially fast if we assume that the random walk has either finite variance or belongs to the domain of attraction of a stationary of a stable distribution with alpha between 1 and 2. So let me just conclude saying that so the biggest problem that we cannot prove any other convergence, and consequently we cannot even prove uniqueness of a station distribution unless we have these strong assumptions. But let me also say that this is exactly the same standing in the other model I showed you in the beginning for oscillating random walks, which is, I recall, the Markov chain which behaves as one random walk when it's above and as another random walk when it's below. So the same type of sequence, well, of course it's different, but morally it's not too far. And even for this oscillator random walk, there is no general convergence result. So there were few works in the end of 70s, but none of them claims a general convergence. So these are two not equivalent but similar convergence problems which are still open. So, and we also have a feeling that there is some theory which is missing, which should be behind this, which is a room for everyone to contribute. Okay, so let me stop here. Stability of overshoots of zero mean random walks. So this is a joint work with Alex, which is almost finished. So it's the first paper. So basically, what the talk is about. So let's introduce the main object as n, which is a random walk, which is a sequence of this form. So here the xn's are IID increments, and then let me assume immediately that the increments are zero mean. So in particular, the random walk is recurrent, so which means that it will hit every open set for infinitely many times. And what's important that the random walk starts at some S0, which you should not think that it's zero, but that's a random variable which is independent with the increments. And I will be interested in the following sequence. So let me introduce t0 as 0, and then for every positive integer n, I'm introducing t1, which is the minimum of k larger than tn, so such that sk minus 1 is strictly negative, sk is slightly is non-negative. So this is the these tn's are the moments when the random walk up crosses the zero level. So now, in any way, I will need a picture. So let me draw a picture for convenience. So somehow this is where my time goes. So this is a graph of Sn. So it starts as some S naught. So then it does the following thing. So of course it's a discrete time process, but I'm drawing a continuous trajectory just for the reasons of painting faster. But I need the moments of upcrossing. So, and at these moments I show the breaks in the trajectory. So on this picture, this moment is t1. So then like this. So then makes a jump and so on. So on this picture, so this moment is t2 and and so on. So these are the moments of upcrossings, and I'm interested in the sequence of overshots. So I'm introducing O n as the value of the walk at upcrossings. So these are overshots. So on this picture, so this is O1, this is O2. So this is the main object of this talk. So obviously, if you look at this, at the sequence, so this is a Markov chain. So because basically, once you know where you start from, you start your random walk at this point, and then you follow until it upcrosses. Then this overshot from this starting point gives you the second value, and so on. So this is a Markov chain, and alternatively, so you could have considered the sequence of undershots, which is the value at the preceding time step, and then I'm reverting the sign. Just to make it positive. So in this picture, this is U1, and this is U2. This is something strictly positive, and these overshots are non-negative. So these are the main objects I need, and so the questions I study in this talk will be the following ones. So this is a Markov chain. Does it have a station distribution? Is the station distribution unique? Is there convergence to this station distribution in a certain sense? And are there any bounds on the rate of convergence? So what's important that I want to solve the problem in full generality. So apparently, let me go ahead and say that we don't have answers to most of the questions in full generality. So, of course, once the problem is here, you might ask that this is something which looks really classical, one-dimensional random walk, zero mean, so convergence of overshot. Why people care? So first of all, that's an interesting problem. So that's item number 0 in my motivation list, and surprisingly, there is no result of this sort, which works in full generality. So the other motivations we had. So first, there are connections to integrated random walks. So that's it. So there is a certain class of problems related to these random sequences, which I worked on. And basically, the technique used in that area was to take a trajectory of a true random walk, then partition it according to these upcrossings. So then you split the trajectory into what we call cycles. And so it is really helpful to work with these cycles, which probably stabilize in a certain sense. So which are much more understandable than the original random walk for certain purposes. So it would be nice to have stationary distribution. So here, which will make all cycles to be stationary. So that's one motivation. So the second motivation is that this question is obviously connected to local times. So apparently there is a result by Perkins in 1982, which says that Now I need the discrete local time, so let me introduce L n as the maximum k, such that tk is less than or equal than n. This is just the number of crossings on the interval from 1 to n. So then the result of Perkins is saying that if you take the following sum, so now we are summing the values of the overshot of zero level, plus, so I need to introduce another notation, so I need to actually consider all up crossings rather than all level crossings rather than just up crossings. So if I introduce the analogous variables up and down arrow, and so on, and if I look at such sums, then this sum, the sums of absolute values of all overshots over the zero level at all up crossings up to time, at all level crossings up to time n, so then this normalized sum converges weakly to the local time of a standard Brownian motion at point 0 at time 1. And this is, of course, under the assumption that the increments of the random walk have finite variance. So this is a thick invariant principle for local times, for the local time of the random walk at level 0. What is a little bit unclear about, okay, so then I need to divide by the standard deviation, so that in this way it's true. So what is, in this result, you see that there is summation of our Markov chain of overshots at up crossings, a similar Markov chain for down crossings. So basically, you should think that these are almost the same. But it would be more natural to think about local times as just the number of level crossings. So there are some extra terms here. So, and obviously it would be nice to get a limit theorem of this sort from there. But everything is based on the stabilization properties of these two chains. So if the low flash number holds, then we will get this result. But surprisingly, since this year, so this is the best result known to us on convergence of local types of random walks. So the point is that this Markov chain appears here. And so there are similar models which are not so far from this Markov chain of overshots. So let me let me just say about what is called oscillating random walk. Formally, it's not a random walk, but it's a Markov chain. It was first considered by Kemperman in 1974, and basically, so it's a Markov chain with the following transition probability. So the probability getting from x to dy is given by probability that some random variable x plus belongs to dy minus x when x is non-negative, and similar probability for another random variable x y minus when x is negative. So basically, it's the same as as a random walk, but there are two types of distribution. So if it's above level 0, then the jumps are according to the law of y plus. If it's below 0, the jumps are according to y minus. So then the assumptions on y plus and y minus are that the expectation of y plus is negative, the expectation of y minus is positive. So basically, when your chain is above 0 level, it has a drift towards 0. When it's below 0, it has again a drift towards 0. So why is such a sequence of oscillator and walk related to our question? Because obviously, if you think about our random walk, we started at some level, so then let's say suppose it goes up, then at a certain point it goes below this level, so then you take this as a new level, so this probably goes up and then it goes down again, then probably goes down again, and then eventually, let's say, it becomes negative. So if you look at the rarified Markov chain of these values, so these Markov, this actually is a new random walk, which is called the random walk composed of the heights of the original random walk. So this corresponds to this part, but then if you become negative, and if you think about returning towards 0 and looking at the new levels when you exceed the old levels, so this gives you this part. So somehow this oscillating random walk can be extracted from the original random walk by combining the chain of descending random heights and ascending random heights. So these are the relations of our question to the known models, and it's probably a good time for the results. First result is on the stationary distribution. So I'm going to present you. So is it okay to write on this board? Or should I?
Maybe you can write there as well.
So the other one is more purple. Yes. Okay. So I'm going to present you a stationary distribution for this chain given in a very explicit form. Before I do this, so let's agree on some particularities. So basically, there are two types of random variables which are widely used in renewal theory, and which are useful for statement of our results. So we say that our increments, the distribution of increments of our random walk is arithmetic with step D. If D is a maximum of the values such that X belongs to the integer lattice scaled by D. If D is a maximum number among B prime such that we have this relation. So the maximum size of the lattice such that the random variable lives on this lattice. If such a number exists. And if such number does not exist, then the distribution is called arithmetic. So basically we'll consider two cases. Now we define state space X of our Markov chain. So, and we define it as the scaled lattice in the arithmetic case, and just the half line in the non-arithmetic case. Right? So then let me put the measure on this space. So I'm introducing the measure lambda plus, so which I define as, so that's the measure on our state space of our Markov chain. So I define it as the Lebesgue measure in the non-arithmetic case, and times d times the counting measure if the chain is d-arithmetic. So this is the measure, and I will be always assuming that my random walk starts in this state space D. So if it starts there, then it stays there. Basically, by the definition of our state space. So essentially, there are two cases: lattice or arithmetic and non-lattice. So for the, I'm presenting both cases because I want to show that the results are general. But in principle, for understanding, you can focus only on non-arithmetic case. Okay, good. So now I'm defining the measure. So the measure pi plus. So the measure on this space X as, well, I take some normalization constant, then I take this density, so the probability that X is larger than, the increment is larger than X, times our reference measure, which is either the Lebesgue or just the counting measure on the discrete lattice. So that's my measure pi plus. So this measure is actually quite known for the ones who work in renewal theory, and it appears on two occasions. So first of all, it's the stationary distribution for the process of residual lifetimes, and second, it's the limiting distribution for the process of residual lifetimes. And actually it also appears in the context of oscillating unknowns. So now, given this measure written down explicitly, I can give the first theorem. So the first theorem says that pi plus is a stationary distribution of our chain of overshots. So now let me explain what's the difficulty in this result. So we are given a Markov chain which looks to be nice in a certain sense. So the natural question, of course, is to find its station distribution, whether it exists or not. So you assume that yes, it exists. But if you try to prove to use some general methods for this Markov chain to prove that it has some station distribution, then everything which we tried actually failed, because in general setting, this Markov chain doesn't have the Feldman property. So its transition probabilities in general are not continuous with respect to the starting point. So this breaks down the usability of general ideas, of general statements one uses for existence of a station distribution. And then we were lucky enough to find this station distribution in an explicit form. So on one side, it's not of great surprise that such distribution appears, because it's known for people from renewal theory. On the other hand, it's very hard, so we didn't succeed to find the direct connection between the two. So how did we find such distribution? So we actually were relying on a theorem authored by Borodin and Ibragimov, the theorem from late 90s. So that's a limit theorem for additive functionals of two consecutive values of Markov chain. So why two consecutive values? Because if you, let's say, if you want to track this event of level crossing, then you need to know two values of a Markov chain or of a random walk. You need to know that one value was before level 0, so below 0 level, and the consecutive value was above 0 level. So that's how additive functionals of consecutive steps appear. So, and it was possible to use a certain theorem which applied under restrictive setting. So it applied only for integer valued random walks, and after some computations we obtained this formula for the station distribution. But because this station distribution is known and universal, so we assume that it's also stationary for any random walk with no other assumptions rather than being zero mean. So, and because we like this this result, I want to present a short explanation why this is the station distribution. Let me try to do so. Basically, I'm going to argue why this is a station distribution. So far, I'm not claiming that this is a unique station distribution. So, and how the argument goes. So, I want to introduce two auxiliary Markov chains. I need two auxiliary transition kernels, Q and P. So, and both Q kernels are defining Markov chains on our state space. So just think about continuous case. So the state space is just positive half line. And so the first Markov chain does the following. So it is the conditional probability of x1 belonging to dy plus x, given that x1 is larger than x. So this Q kernel, it actually corresponds to the up crossing. It actually describes this part of the trajectory, which corresponds to the increment which does the up crossing. So, and the second transitional kernel which I want, it is just the distribution of this U1, which is the undershot at the first up crossing, which was something positive by definition. And so the first Markov chain, so the second Markov chain with the second transition kernel is given by these points. So in terms of these two transition kernels, or recurrently in terms of these two transition probabilities, so for every starting distribution mu, so the law of the first overshot is given by the product of these two kernels. So mu times P times Q. So if you want to get this distribution here, you just start according to mu. So then you apply the P kernel and you get the distribution of the undershot, and then you force your trajectory to jump over, which is done according to this kernel Q. And now the main statement, which gives immediately the stationarity of this very distribution phi plus, is that so both P and Q kernels are reversible with respect to this measure pi plus. So this means, so let me remind the definition. So this means that the following condition, which is called the detailed bound condition, is satisfied. P of dx times, let's say, q x dy is the same, stays the same when you swap x and y. P of dy times q of y dx. And you want this detailed bound condition to hold for every x and y in the state space. So in particular, so this reversibility implies that you can reverse time in your Markov chain. So which means that, let's say, this implies that if you start your chain at this distribution pi, then the law of, let's say, Q0, Q1 will be the same as Q1, Q0. But of course it means much more than this, but if you never saw reversibility, think about property which helps you to reverse time. So this is the key property for the stationarity of this distribution. And so this property has nothing to do with the way we discovered this distribution, but it's a way to prove that it's stationary, literally under no assumption, rather than having zero mean for the original renewal. So why this implies stationarity? Because it's well known that every reversible Markov chain has this measure as the station distribution. So if I start my Markov chain according to pi plus, then at this step, so this value is pi plus again, because it's reversible for p, then applying it again for q gives me pi plus again. So from reversibility, the stationarity follows immediately. So now let's see how the reversibility works. So first, let's see it for q. And basically, if you rewrite this side for q, so what shall we have? So we will have, so first of all, think about the non-arithmetic case. So then this reference measure is just the Lebesgue measure, right? So then when I rewrite the left-hand side, so I will have some constant times dx, and then, so this term here, which cancels out this conditioning here. So and then eventually I end up with this expression for the left-hand side. So and you see, so it's actually easy to see, and if you don't believe, think that x1 has density, although it must not. That this is so this expression is symmetric with respect to swapping x and y. So this gives you immediately the reversibility of the Q chain. And with the P chain, it's slightly more tricky. So so this is actually the main point of this proposition. And because I'm running out of time, I just want to claim that the things work. Just to show just to explain in 2 words the main idea. So we need to argue this reversibility of the P chain. So basically, what does this mean? So we mean it means that we fix the in this expression. So think substituting P instead of Q. So we have the starting point x. So we want our trajectory to belong to some dy, and I'm taking the minus sign back because I changed the sign in the definition. So, and now what happens if I look at this expression? So first of all, this term pi plus dx, so it gives me some constant dx times the probability that x1 is larger than x. So this is from pi plus. And then I'm just writing down the law of this undershot starting from here. So what I'm doing, I'm taking summation over all possible lengths over all possible values of this time. And so then, what should I do then? I know that because this is the last value before my chain up crosses, I know that, so this probability must be there because my chain up crosses. And then I'm fixing this endpoint here. So basically, I know that, so fixing this endpoint here gives me that sk minus s naught. So this difference in height between the endpoint at time k and the starting point at time 0. So it must be nothing but negative dy minus x. So once I fix the endpoint, I will have a random mode bridge once the endpoints are fixed. And what's the condition? So the condition is that the random walk bridge of length k down crosses